Okay, let's start the fourth chapter, random walks and mobile entities. So random walks, this category of models, they can be used to address the movement of different entities. For example, pedestrian, for example, animals, right? And transportation, okay? So their movement in geospace. Of course, some people they're using random walk models to simulate virtual entities and their movement in virtual space. For example, the movement of a person on the internet, right? It's a virtual space, and when you are talking about browsing internet, you are not physically on the internet, right? Your device, the device you are using is on the internet, okay? Your movement on the internet on this within this virtual space can also be addressed by random walk models, okay? So the GIS applications of RWs include pedestrian movement, evacuations in emergency situations, animal movement and animal foraging behavior, and traffic. Okay, and in other realms, I mean, besides GIS, can be random walks (RWs) can be used to simulate random motion for of molecules in liquids and gases, even stock market and finance, and vision science, which means the movement of your eyes. So here in this course, let's talk about um, random walks and their applications in GIS. Okay, so RWs and mobility situation, there are different types of them. There are different types of random walk models. Okay, in this course, we're going to talk about simple random walks, which is the very fundamental one, very basic one. And then random walks with variable step length. And then more purposeful random walks, which is called correlated random walks or correlated walks. And then levy flats. Levy flats, later you will see that it's a very universal model to simulate the behaviors of animals when they're trying to find food. And also you will see that it's a very good model to simulate people's daily movement. Okay, and also foraging and searching behavior. I mentioned this before. When animals they're trying to find food, they would always try to be efficient, which means use the least time to find as more resources as possible, like food, water, or any other resources. So what's the strategy here? Obviously, they're not purely randomly moving around and searching for food, for other resources. What's the best strategy? And also moving entities and landscape interaction, and also flocking, entity interaction. You say, how is random walks associated with flocking? So flocking means the movement of a bunch of birds, right? Of birds. When you say a group of birds, they're flying in the sky, there is always this pattern that all these birds, they are not too close to each other. So they do not run into each other. And they are not very far away from each other to make sure that they are a group. They are flying to the same destination. And in order to keep themselves safe from predators, from bigger birds, they have to get close enough. So not too far away, not too close. So how to implement this behavior, this flocking behavior, okay? Well, of course, different people, they have different methods to address it, but random walk models, later you will say that they're pretty good for the simulating of flocking behavior, okay? Okay, let's start with the very basic random walk, okay? It's called basic random walks. It's not realistic because it's too simple, but it's a pretty good null model. It's a starting point. You can also consider this as a reference, as a baseline, So we have two types of them, two types of basic random walks. The first type is called lattice random walk. So RW restricted to discrete locations, or you can say restricted to a lattice with a lot of cells, right? And Walker starts at 0, 0. Of course, this 0, 0 can be any cell on this lattice as long as it is the original location of this Walker. Usually it's in the center of this lattice, but it's not restricted to the center of the lattice, okay? At each tick, this walker randomly moves in one of 4 cardinal directions with a unit step length, okay? So here the simplicity, you can say, only 4 directions. Choose one from 4 directions to move. And also for each step, it moves for a unit length. You can on a lattice, usually we say a unit distance, a unit length is the distance between one cell to its neighbor cell's centroid, from one centroid to another centroid. And this cell should be neighbors using Von Neumann neighborhood, which means neighbors only on 4 cardinal directions. Okay, so choose a direction, north, south, east, or west, and move 1 unit step along that direction. Okay, this is simple enough, cannot be simpler, right? And next step, we call it simple random walk instead of lattice random walk. It's more complex than lattice random walk in terms of the direction. Same as above, but Walker can move in any direction on the interval from 0 to 2 pi. So 0 is 0 degree, 2 pi is 360 degree radians. Of course, when I say degree, it's not, it's in degree unit, but here 0 to 2 pi is radians. So here it means that if your direction is 0, it means that you will go along the direction that you are now facing, which means there is no change of direction. If it is other direction, then you choose a direction from 0 to 2 pi. Okay, of course, you can use different methods to choose a direction, pure random or following a specific distribution. But here, the tricky part is that we have 2 types of brackets here. On the left side, we have a square bracket, which means that 0 is included. On the right side, we have a regular bracket, which means that 2 pi, the specific value is not included. Why? Because if you are moving on a direction of 2 pi, you are actually turning 360 degrees, which means you are turning back to the same direction when you are facing right now. You're facing right now. So 2 pi is excluded, but 0 is included because they are actually the same thing in terms of direction, right? So lattice random walk, only 4 directions. Simple random walk, more options, infinite options, right? From 0 to 2 pi, you can choose any angle, right? And usually, when we're talking about angle in this course, it's clockwise. It's clockwise, which means that if you are facing north right now, right, it's 0. When you are talking about a direction of half pi, which is 90 degree, okay, should you turn counterclockwise or clockwise? In this course, clockwise, which means if you are now facing north and the direction for the next step is half pi, then you should turn to the right because it's clockwise, right? Turn to the right for 90 degrees. And next step, you are going which direction? East, right? Okay, so you need to be clear with this. So this is an example of what? Of lattice random walk, right? Lattice random walk, only 4 directions. Okay, only 4 directions. That's the reason why that we have a lot of squares here, because for this walker, you can only choose a cardinal direction to walk. A simple 1,000 step random walk on a lattice. The open circle indicates the start location. Open circle right here. That is 0, 0. Like I said, 0, 0 can be anywhere on this lattice as long as it is the starting location of the walker. Well, the black circle shows where the walk has reached after 1,000 steps. This is black. This is a black circle. You can see that after 1,000 steps, this walker did not move very far away from its starting location, right? Why? Because at each step, the location was randomly chosen. So it's very likely that this walker experienced a lot of turning back and go back. And then maybe next step, still going back. And maybe after several steps, it is going along another direction, right? So if you measure the distance between the starting location and the ending location, it's not very far away, right? And the end points of 500 random walks of 1,000 steps and their density. You can say each point here is a what? The end point is an end point. So let's just assume, there were 500 simulations. And for each simulation, the walker started from the very center of the lattice, because you can say this is 0 for vertical axis, this is 0 for horizontal axis. So the starting point is always in the center of the lattice. So after 1,000 steps, there is a circle, because each circle is a endpoint, right? So, and we repeat this 500 times. So this is the trajectory cloud of this 500 walks of 1,000 steps. So you can say most of them, they are very close to the center of the lattice. They are very close to the starting point, which means that, okay, if you are using this lattice random walk, you're not going to go very far away from your starting point, according to our 500 simulations, because most of these endpoints, they're very close to the center. Some of them, there are outliers. For example, this one, this time this walker made very far away from the center. This one, also another outlier. Okay, in this simulation, this walker also made very far away, went very far away. Okay, but they are, after all, outliers. Most of the walks didn't move very far away from the center, from the starting point. Okay, so this is a spatial pattern. And yeah, there is a model in your model library, textbook model library for random walk. You can go to this model and play with it. I've made some explanations for different parameters. Okay, next type of random walks. Random walks with variable step length. I think the name is obvious enough. So here, step length is not 1 unit anymore. It is random. It is random. Like I said, you can just use different probability distributions to decide the peak of step length. Okay, for example, normally distributed step length, simple random walk with step length drawn from a normal distribution with mean 0 and standard deviation equals mean step length. Or you can use another distribution, probability distribution, exponentially distributed step lengths. Simple random walk with step lengths drawn from not a normal distribution, but exponential distribution with mean equals mean step length. Okay, mean step length is something you can decide in this model. And here is a normal distribution. What does it mean? It means that, okay, now I don't want to set each step as 1 unit length. This length can be shorter, can be longer, but how to decide? We use normal distribution to decide. Okay, what's the meaning of a normal distribution? The normal distribution addresses a fact that for a lot of phenomena, when you are picking a specific value from this phenomena, it's most likely you will have a value not too large, not too small, but very close to the mean value of this phenomena, of this data set. This mean value, let's just assume it's mu. And the standard deviation of this group of data of this phenomenon is delta. Okay, so what does it mean? It means that for each step, you need to randomly choose a distance for the next step from this normal distribution. Okay, from this normal distribution. And according to this normal distribution, you are most likely to choose a distance that is not very far, not very short, but okay in the center. It's possible you could choose a very short distance or a very long distance, but the probability is pretty low. Okay. Similarly, for exponential distribution, it's the same. It's the same. The vertical axis is for probability. More strictly, more accurately, it's actually probability density. But that's another word in statistical class, and I just don't want to confuse you. You can in this course simply consider this as the probability instead of probability density. But if you're interested in the difference between them, you can do some research online. Okay, I mean, let's get back to the exponential distribution. Here we have different types of exponential distribution with different parameters lambda. Okay, and the idea here is the same, right? X is for distance. Px is the probability density that a specific value x will be chosen. Okay, so the key point here is that we have a variable step length for each step, and this length can be picked, can be drawn from a distribution, normal distribution, exponential distribution, or any other distribution you want. Okay, and let's talk about proportionality property of RWs with variable step length. Okay, the root mean square distance grows in proportional to the square root of the number of steps, as long as the variance of step length is finite. Which means that the distribution you are using is light tail distribution. Okay, so here is what is the distance. R is the expected straight line distance, not the distance along the walking path between start and end locations. T is number of steps. So this formula here is actually the mathematical expression of the sentence here. The root mean square of the distance between start point and end point is correlated with the square root of time. Time here is actually equal to step. because after each tick, there is a step. And each tick is an expression of time in net logo, right? Which means what? The longer the time, the longer the distance. But it's not a simple equal relationship. Okay, they're proportionally related to each other. This is the specific mathematical formula to address this relationship between time and the straight line distance between start point and end point. Okay, and about light tail distribution and heavy tail distribution. So normal distribution here, the blue curve here is a light tail distribution. You can see that there is a tail on the right, there is another tail on the left, but they intersect with the x-axis quickly, and the tail is not too long. There is another distribution here is called Cauchy distribution. It's a red curve here. If you compare it with the normal distribution, there are also two tails on the right, on the left, but these two tails, they are longer than normal distribution and they do not easily intersect with x-axis. So Cauchy distribution is a what? Is a heavy tail distribution. Normal distribution is a light tail distribution. Okay, for this course, you just need to know this: light tail and heavy tail distribution. As the distribution you use to draw distance for each step is a light tail distribution, this relationship here exists. If it is not light tail distribution, then say no to this relationship between time and R. Okay? Okay, let's continue. Next one is called correlated walks or correlated RW. It's a more purposeful RW. Why? Let's say it. Bias the walk direction by selecting a random turn angle relative to the previous step. What does it mean? It means that for each step, the direction is not purely random anymore. You need to choose a turn angle based on the previous step, which means that the direction of the previous step will affect the direction of the next step, because the next step's direction is within a specific turn angle of the direction of the previous step. Okay, so every two steps, if they're adjacent to each other, the later one's direction is based on the previous one. Okay, small angles represent more purposeful movement. Small angles means that the direction of the next step is similar to the direction of the previous step, which means it's more purposeful, which means that it's not random. Because if that is the pure random walk, for the last step, it could be the direction could be east, and the next step could be west, totally opposite direction. And it's not purposeful, of course, because it doesn't make sense if you have a purpose. You went to the east and suddenly you went to the west. It doesn't look like purposeful. But if you are using correlated walks, the previous step was along east, right? And the next step, the direction of the next step should be within a specific random turn angle range of the previous step, which means that the next step could be somewhere biased, some direction biased from pure east, but not likely to be pure west, which means that these two steps, they are more purposeful than the pure random walks, pure random steps. Okay, that's why it's called correlated walks or purposeful RW. Okay, And you can also implement it in this model 4.1. Okay, you can choose correlated directions for type of walk. And here we have different standard deviation angles, or let's just say here we have 3 normal distributions with different means and standard deviation. So pick one walker and vary the standard deviation angle from 1 to 90. Okay, so what does it mean? Here we're using normal distribution not to decide the length of step. We're here using it to decide the angle for the next step, the turn angle. Okay, why am I showing these three normal distributions? Because you can say that with the same mean, which is 10, we have 3 normal distributions with totally different shapes. If the standard deviation is 1, which is the green curve, you can say that the possible values varies within a relatively smaller range, maybe from 7 to 13. And if the standard deviation is doubled, which is 2, then the value varies in a very large range from 4 to 16, to more than 16, less than 4. If you triple the standard deviation, it's not 1 anymore, it's 3. You can see that an even larger range exists for the possible values. Now it's from maybe less than 1 to more than 19. What does it mean? The larger the standard deviation angle, the larger possible value range you have for your turn angle. So if you want your walk to be more purposeful, should you use a smaller standard deviation or larger standard deviation? Of course, a smaller one. Because if you use a smaller one, the turn angle for the next step only varies within this small range, which means that the direction of the next step will be very similar to the direction of the former step, of the previous step. Instead of that, if you use a standard deviation angle, or say standard deviation value of 3, if you assign 3 to the as a standard deviation, you will have this red curve for your normal distribution, which means that the turn angle you can choose, the system will choose for you, will vary from somewhere below 1 to somewhere above 19, which means that the possible turn angle for the next step could be very small, could be very large, which means that the next step is less purposeful because the turn angle is not as stable as the turn angle you would choose from a normal distribution with a standard deviation of only 1. Okay, so if you set it to a small value, you will observe, you should expect a relatively purpose walk. If you set it to a very huge value, you should expect that the walker is purposeful, is more purposeful than simple random walk. But now, it's not that purposeful as the one with the standard deviation of 1. It will wander within a small area sometimes, and sometimes it will just go straight. Okay, so this is the explanation. This is the influence of choosing different standard deviations for your what? For your turn angle. But in order to see the pattern, I would suggest go to this model and play with it a little bit. Okay, there are different types of walk. There are different types of walk. And the correlated RW properties, okay? Proportionality properties still holds since correlation fades over time. What does it mean? What does it mean? Okay. Let's just do this. I'll stop here. And I will just start introducing this part about the correlated random walk properties from the start of the next video. Okay, this video is long enough information for you. Thank you.